When operating complex robotics, you need a live, dynamic environment. You want the machine executing tasks seamlessly while you process the raw telemetry it generates. To maintain operational efficiency and ensure system safety, real-time monitoring is critical. That is why today, we are going to build a custom graphical dashboard from scratch to track our robot's performance. Before we write a single line of code, you need 3 specific components ready to go. First, a working installation of the Robot Operating System, or ROS. Second, you must have an active Python environment set up. And third, install the required libraries, ROS.py, tkinter, and matplotln. Once everything is installed, we can move away from reading raw text scrolling in a terminal. Transitioning to a structured graphical interface gives the operator a clear, immediate view of how the system is performing during a deployment. Step 1 in our build is establishing a connection to the system network. To do this, we need to write a dedicated subscriber node script in Python. We start by importing the necessary tools. We bring in ROSB to interact with the system, and we import string from std messages so we can fetch standard text messages from the network. Next, we create a listener function. This function initializes our node, giving it a unique name, and then formally subscribes it to a specific topic. Let's call it chatter, so it knows exactly where to listen for incoming data. To verify that our node is actively listening, we launch it alongside a basic publisher module that sends out a steady stream of test messages. If the connection is successful, you will see your terminal rapidly printing out "I heard," followed by the data packet. This confirms our node is intercepting the live messages exactly as intended. We have confirmed a pulse in the network. However, raw terminal text is difficult to track over time, which is why we must now build a visual container for this data. Now that our network logic is working, we shift our focus to constructing the graphical user interface using tkinter, Python's standard GUI framework. We start by instantiating the primary root window. Inside that window, we define a basic string variable and pack a simple text label into the frame to display our text. A static window won't help us monitor live data. We have to implement an update loop, a function that forces the interface to refresh its contents consistently every single second. This small, minimalist window shows the result of testing our standalone script. The text updates automatically on the screen, proving our visual loop is functioning correctly. Right now, this visual shell is an isolated vessel. Before we can feed it our live network messages, we have to resolve a conflict between our background listener and our visual loop. When merging these 2 components, you will likely encounter the most common failure point in dashboard development, the blocking nature of application loops. Both the ROS listener and Tinker GUI demand exclusive attention. If forced into a single sequence, they block each other, causing a crash. To solve this concurrency problem, Python's threading library places them onto separate execution tracks so they can run simultaneously. We handle this by wrapping our network listener inside a custom thread. We execute the start command for this thread right before launching the main visual interface. Running the program now, we see the interface updates with live network messages smoothly. The system remains completely responsive, with 0 freezing. Effectively managing these concurrent processes is what ensures the interface stays live and responsive, even when the data flow is at its heaviest. Step 3 is upgrading the interface. Raw text readouts are a start, but we can turn them into dynamic graphical charts using the matplotlib library. We begin by defining a basic figure and a set of plotting axes. This creates the exact container that will hold and scale our incoming numerical values. To get this graph into our tkinter window, we use a specific matplot backend tool called Figure Canvas TK Aggregate. This mechanism embeds our graphical figure directly into the master interface canvas. This completed dashboard shows a clear, rendered line graph charting the sequential data points live. Our standalone window is now a fully functional visual monitor. Translating abstract numerical feeds into immediate visual trends allows an operator to detect spikes, drops, and anomalies the instant they occur. We have successfully built a bridge. We connected deep network topics to a responsive, human-readable Python interface. With the final ecosystem operating, we get perfect synchronization. The mechanical actions of the robot are immediately reflected in the live visualization of its output. Because this architecture is modular, you can scale it immediately. You can plug in CPU health monitors, track memory status, or even integrate RViz for three-dimensional data rendering. By designing your own dashboard architecture, you create a custom environment that matches the specific telemetry and monitoring needs of your robotic application.